Hi everyone, my name is Lara Díaz-García and I am a PhD student at the University of Strathclyde in Glasgow, Scotland. This is a presentation for my poster towards a bio-inspired acoustic sensor, Achroia Grisella's ear. Before I begin, I want to thank the IEEE Sensors 2021 conference for giving me the chance to present my work. Achroia Grisella is a nocturnal moth capable of hearing. It uses its ability both for predator avoidance and for mating, the latter being unusual for Lepidoptera, that is, butterflies and moths. The male specimens produce clicks of 100 kHz and the females make their way to them, not in an optimal way, but efficiently enough to guarantee mating. Due to their small size, about 13 millimeters on average, their tympana are separated roughly less than 600 microns. No significant time, intensity, or phase difference could arise for the moth to perform binaural localization. No connection between the tympana has been observed either. Furthermore, experiments where one of their tympana were pierced resulted in the moths still managing to locate the sound source, albeit with more difficulties. This implies that directionality is granted by just one tympanum, and it must be entirely due to its morphology. That is our working hypothesis. Which brings us to our goal, to develop a model with similar behavior to the moth's tympanum and to 3D print devices that agree with said model. In other words, directionality on a small scale and a small design cost. So what does the actual problem look like? It can be described in terms of the shape and behavior of the tympanum. On the left, we can see an outline of the tympanum morphology, elliptical in shape, with two sections of different thicknesses and a neuron cluster attached directly to the thin section, indicated by the blue dot. On the right, we see an animation for the frequency response from an actual specimen. We see a large displacement peak close to the neuron attachment point, and it moves out of phase with a surrounding ring and a broad bump in the thick section. We consider an increasingly complex model that improves the resemblance to our natural system. Then we consider our model through equations, COMSOL simulation, and 3D printing, and then compare the three. So let's skip now to the simulation results for the most complex model. On the top, we are looking at the 6th resonance frequency of our plate. The shape is similar to the description of the tympanum displacement for Achroia Grisella that we just went over just now, which is a good sign. On the bottom left, we can see a 3D printed elliptical plate with two different thicknesses. 3D printing was done with an original Prusa SL1 that uses a stereolithography and a commercial resin. On the bottom right, we can see a table containing the comparison of the first few resonance frequencies of COMSOL and printed devices for 3 models. We can see that they are in good agreement as well. So to sum it up, our model seems to be a good imitation of the actual behavior of the moth's tympanum, and furthermore, the 3D printed parts frequency responses are in agreement with simulations. Further work will include measuring the directional response in simulation and actual 3D printed parts, and exploring other factors like damping, etc. Thank you for watching, and thanks again to IEEE Sensors 2021.